what better topic than to have around beaming 5G from the stratosphere? Amazing topic, and I think you're going to find it really interesting. I'd like to introduce first Gary Kemp from Cambridge Consultants. Over to you, Gary.
Thank you very much. Morning, everybody. Thank you for coming to listen to us today. We're going to talk about an exciting project that we've been involved in since 2015. I'm here today with our client from Stratospheric Platforms Ltd, Kevin Bean, who's Chief Technology Officer of SPL. Is the clicker working? Let me try that. There we go. So so beaming 5G from the stratosphere. So the challenge is, how do we roll out 5G everywhere, not just in the cities, but in the harder to reach areas, in remote places where it's really challenging to lay fiber, it's expensive and time consuming to provide ground terrestrial based infrastructure to give a high level of service to the whole population of a country, not just concentrating on the cities, but in the Highlands of Scotland, in remote parts of Australia, wherever it could be. So that's the challenge that we have set. So Stratospheric Platforms is a company based in the UK, and Kevin's going to talk to you a little bit about their vision, and I'm going to talk to you about our role in helping to develop the technology that addresses this challenge. So Cambridge Consultants is part of Capgemini Invent. We're about 850 people, headquartered in Cambridge, UK, and with offices in the US and in Singapore and Tokyo. We do development of next generation product systems and services for clients who are highly ambitious and want to create something that's never been done before. And we have a big range of mixture of engineering, design and development skills that we can bring together to create breakthrough systems. And this is a great example of how we apply ourselves to those sorts of challenges. So now I'd like to hand over to Kevin from Stratospheric Platforms.
Hello, and thank you, Gary. And it's a pleasure to invite me here to this show. So I'm Kevin Bean. I'm Kevin Bean, the Chief Technical Officer for Stratospheric Platforms. As a company, we've been around for 6 years, and our purpose, exactly as Gary said, is to provide high quality, high data rate, high capacity 5G to both rural and semi-urban areas. This works. So what's the breakthrough? Why does Stratospheric exist? And it really is, it's all about this picture. The role of Stratospheric Platforms is to provide high data capacity, both for 5G and fixed wireless access in remote, rural and semi-urban regions. If you see here, you can see this is a 15,000 square kilometer footprint from a single Stratomast aircraft that provides up to 400 to 500 cells, each cell providing around 200 megabits per second download. One high-altitude platform, therefore, is capable of placing around 450 masts, depending on the terrain beneath the aircraft. It's a huge amount of power. The other thing we were keen to make sure, and Gary will talk more about the antenna in a minute, is that we were just part of the telco terrestrial infrastructure. We are waveform agnostic, 3G, 4G, 5G, and from a terrestrial tower viewpoint, we're just simply a mast, but a mast that happens to be at 60,000 feet. So what's unique about us? First of all, we have a lot of power. We're a hydrogen power platform. We have over 20 kilowatts of power. That allows us to actually operate as if we're a terrestrial system connecting to over 500,000 customers. We have very low latency compared to satellites. We've measured the latency from the stratosphere. It's 1 millisecond latency. And also, other unique selling point is because we're hydrogen, we do not pollute the atmosphere. So we provide a lot of power, similar to a normal aviation gasoline aircraft, but we're able to provide 20 kilowatts and carry over 120 kilograms worth of payload. Again, Gary will talk more about the payload shortly. Other important things about once you're a large aircraft, you can carry a lot of payload. We're able to start looking to future as well, open RAN and put an edge processing on the aircraft, again, to increase the performance of the system and become a neutral host system as well, so multiple operators can use a single aircraft. Just a quick comparison against satellites, why we're unique and different to satellites. As I've already mentioned, we have a very low latency. We can provide very large average download speeds to operators, very high upload speeds from a handset. That's unlike most satellite systems, we're just a normal mobile phone. And because we have a very large aperture payload, a lot of power, we're equivalent to a terrestrial tower that's 300 to 400 meters away. And we have the most important statistic for me is this throughput per kilometer squared. It's how much capacity we can put on the ground. And over that 15,000 square kilometers, on average, we can do 5 megabits per second per kilometer squared, which is 4 to 5 orders of magnitude higher than most satellite systems to handsets. Also, and Gary will talk about it, the payload is very flexible. What's key for us is to make sure that as well as this large average throughput, when you're over a town, we can offer up to 1 gigabit per second per kilometer squared. And this is our first iteration of the payload with minimal bandwidth. As we increase our bandwidth, that's gigabit per second per kilometer squared, maximum data capacity will increase rapidly. And as I said before, it was really important that we could connect to smartphones, allowing you to have a consistent signal anywhere in the world. So where are we? So the aircraft concept has been completed with our partners. It operates on hydrogen. 2 50 kilowatt hydrogen engines provide lots of payload power. The system is able to operate in the stratosphere up to 9 days, allowing us with multiple aircraft to provide continuous 365-day coverage in all weather. And because this is a internal combustion engine powerful aircraft, we can operate with the northern hemisphere in the presence of polar vortices and wind conditions. When we take up a land, rain and lightning strike, the aircraft is designed to operate in those conditions, exactly as if it was a 6-passenger aircraft. So we're certified as a normal 6-passenger aircraft. And as you can see, the high cruise speed is important to us because the other key requirements that was provided to us by our telco partners and investors is we must provide 99.99% availability, the same as a terrestrial system. To do that, we have to be able to fly fast enough so we can live in those solar winds and not be blown off course, which of course would impact our service. So the aircraft is a hydrogen-powered system. One of our key technologies is we actually store the hydrogen in liquid form. We take the liquid hydrogen out of the tanks, and we use that to power the engines. Why do we use liquid hydrogen? 2 reasons. One I've always mentioned, it's green. We only put water in the atmosphere. But very importantly, hydrogen is 3 times lighter per avgas for the amount of energy it stores. So that's the other reason we use hydrogen. It allows us to get these long endurances and provide lots of power to our payloads. This is a study we performed for the UK government. As you can see here, to cover the whole of the UK, we would need just 24 HAPs. And that would mean that we would only need 9 offshore wind farms to power the system. Or, as you can see there, a fairly small area of solar. And that is solar in the UK. Well, of course, it's not that efficient. So in countries with more sun, we would actually need a smaller solar footprint. So a very green system, and we do not need to use much energy because, as Gary explained, the mobile phone handset is almost always in line of sight mode. And because we're a flexible system, which Gary will explain, and we can put the power where is needed, we don't need as much power as a terrestrial system on the ground. In fact, the independent studies said that from the HAP, we would need about 10% power to provide equivalent coverage to a terrestrial system. Gary will talk more about the payload. From a aircraft viewpoint, it's key. It has lots of power and can service lots of customers. And indeed, the whole system at its peak can move around 100 gigabits per second per aircraft. Gary will talk about the payload in detail, but just to explain the scenarios for our business case. Obviously, disaster recovery. At 60,000 feet, if there were a hurricane, the aircraft could fly just behind the hurricane, and you could get coverage to over 500,000 people straight away, even while the hurricane is still blowing, which is great for emergency services. You can see in the center there, to operate as a mobile phone system, Gary again will explain, we can provide different power. So we can provide power over the cities and less power, for example, there in the center over the sea, where you just don't need that capacity. We can also operate on the top right corner and the bottom left corner in fixed wireless access mode, where you put a little MiFi hub on the roof, and then we can provide broadband services without the need to lay cable or fiber. And finally, for autonomy, we can create what's called supercells. So when you're on a road, for example, you enter the cell, you then don't leave, and this is very interesting for autonomy because it reduces the chance of a dropout. And finally, this time last year, we completed the world's first 5G service from the stratosphere with our partners. That was a very small cell, but what it demonstrated is the ability of the waveform to operate from the stratosphere. So we measured the latency. We actually provided 5G calls to not just users in buildings and outside and in cars, users on boats where there is no terrestrial coverage, and also into a helicopter flying around. Again, very difficult for a terrestrial system. So we're now very happy that we understand not only does the technology work, but also that the waveform is suitable for 5G services. And later on this year, there will be further announcements. We will be taking the payload and integrating it with other telco networks to show that we can actually now be fully integrated with telco systems. So with that, I'll hand back over to Gary, who'll talk far more in depth about the actual payload. Thank you.
Thanks, Kevin. So, the engineering challenge of creating a payload that has massive capability to provide coverage over a very wide area and a high level of service is what we were set. It's a multi-dimensional challenge. When you've got an aircraft that's carrying fuel and able to provide a decent amount of electrical power to the payload, it gives you lots of scope to build something that's really has a massive capability. So the challenge is an engineering challenge with many dimensions to it. So creating a very large phased array beamforming antenna system, part of it. But to do that and build something that can be carried by an aircraft, that can survive in the stratosphere, that can be cooled with a very small amount of atmospheric air, that's very cold, very dry, but also on the way up and down from the stratosphere has to go through moist, warmer air and not ice up and still survive all of that and work when it arrives on station. To be lightweight, to be compact enough to be installed in an aircraft, and all of those things make it a really stiff challenge, and that's where we bring all of the sort of capability of Cambridge consultants to bear on such a thing. So here's a rendering of a full-sized array. So that's over 3 meters across, and it has 2,048 individual elements. Every element has a transmit-receive radio behind it. So it's and 2 polarizations. So when you've got such a massive phased array that it's controlled completely digitally. So every element is individually fed from a digital processor. You can be very creative in the way that you form your beams, control your beams, and where you put the service on the ground. And I'll explain a little more. So each one of those patterns you can see, it represents the coverage of one aircraft on the ground. So you can see you can cover a very wide area with just a few aircraft. Yep. Here we've got a little video. As you can see, an aircraft circling around, providing coverage over. This is Brighton, the south of England, and as the aircraft moves around, the digital beamforming system is continuously reshaping and re-steering each of the beams to take out the rotation, the motion of the aircraft, and holding each of the beams fixed on the ground. Those beams can be, each one can be an independent cell, or you can combine multiple beams into a single cell. You can also provide a higher level of service into some of the beams, so you can put the service where the population is on the ground. So increase the level of service where there's a higher population density. You can also control spillover very accurately. So you can see along the coast there, we've got a cutoff of the coverage, and that's important. For example, at national boundaries where you want to minimize spillover into the country next door. You can also shape the beams in exotic ways. So I think one of the pictures that Kevin showed earlier was a beam shaped like the M25 motorway. So when you've got so many elements that you can individually control, you can be very creative with the shapes of the beams. And again, just to emphasize that the whole structure is designed for installation in an airframe. So low profile, lightweight, and all of those things to make it compatible with a large aircraft. And we've built and measured a large array already. So this is in our test chamber in Cambridge, UK. You can see we've done some measurements showing multi-beam, creating multiple simultaneous beams. And the lower plot shows how you can control the side lobes. So we've got 3 different levels of side lobe control on the lower plot. Important, again, to optimize coverage where you do want it and where you don't want it. And the performance, it agrees very closely with theory as well, which is very pleasing. Which means we can now have the tools to plan where we want to create our beams from this large array, and be confident that when you implement that, it's going to do what you want. And here's a system in our test chamber in Cambridge, UK. So the full system, it's built as a set of tiles. So each tile has its own beamforming processor behind it, and a tile is 8 by 8 elements, and you can build up as large an array as you want from the tiles. They all communicate with each other to organize themselves as one large antenna. This is 4 tiles in our test chamber. Next steps with this are to go into flight trials this year in the UK and then in the Middle East. Watch this space, and we'll hopefully come back next year with some results from those trials. And I think that's the end of the presentation. Thank you for listening, and if there are any questions, please.
Hi. Can you, yeah. So you mentioned that you provide direct connectivity to the end user. Therefore, you're using telco spectrum.
Yeah.
So what spectrum? How much bandwidth in terms of megahertz? And what kind of challenges will it create for the telco to manage the radio planning on the ground plus those additional towers from the sky?
Yep. So the system we've built so far is designed to work in bands 1 and 7 LTE, but the same principles can scale to 5G bands as well. Bandwidth of this system is currently 10 megahertz, but will extend to 20. and we can go as wide as 60 in future as well. So is that fair? And how do we coexist with existing telcos?
Just add to that. So when this is not a standalone system, this is fundamentally part of the telco's network. So it's their frequency. We're just a very high level mast. And indeed, the advantage of this technology and our architecture is that from a telco viewpoint, they have their base stations on the ground. Instead of plugging into a mast of 20 meters high, we take the signal, we put it to 60,000 feet. So when it comes to planning, initially it'd be planned like a terrestrial network, but as the future evolves, because the inflexibility of a phased array, we can start looking at events happen. We can move beams around, and also we can start looking at interesting things like the diurnal cycle of people at work, people at home, and so we can then start flexibly changing the power. But initially, we'll plan it like a terrestrial system, but very quickly we'll be able to get more efficiencies through better planning systems.
I brought a prop. This is this is a quarter of one tile, just to give you an idea of the size of things.
Other questions? Fascinating. Thank you, gentlemen. That was great. Thank you so much.